projects. In this video, we are going to explain about the project, which is efficacy of bidirectional LSTM model for network-based anomaly detection. Introduction of the project. In the era of information technology, the secure transmission of crucial data, including voice, images, and sensitive information like banking and personal data, is of paramount importance. The rise of cyber threats necessitates advanced tools and methods for detecting and preventing intrusions. Anomaly detection, identifying patterns that deviate from the norm, is a key component in fortifying cybersecurity. Anomaly detection finds the applications across diverse domains such as business, network security, health monitoring, credit card fraud detection, and fault detection in the critical information systems. Its role in cybersecurity is particularly crucial, offering a robust defense against cyber adversaries seeking unauthorized access or malicious activities. Traditional machine learning based network anomaly detection algorithms, while effective for smaller datasets, faces challenges in the scalability and performance when dealing with the large datasets and complex features. Their efficiency is heavily dependent on the implementation of feature engineering, and the split ratio makes them less suitable for tasks involving extensive datasets and intricate features. Adoption of deep learning techniques recognizing the limitations of traditional approaches. This project leverages deep learning techniques tailored for NSL-KDD data. While convolutional neural network excel in image datasets, our focus shifts to methodologies like long short-term memory, which are LSTM networks, designed to process sequential data inherent in network traffic, effectively capturing and analyzing patterns. Objective of the project. The objective is to design a comprehensive anomaly detection system for a network data, incorporating both traditional machine learning and advanced deep learning techniques. The goal is to create a solution that can effectively identify indicative of anomalies tailored to adapt the unique characteristics of the network traffic data. The goal is to perform an in-depth analysis of the BioLSTM model's performance by systematically experimenting with the parameters such as optimizers, epochs, batch size, and the dataset sizes. This analysis aims to gain insights into how these factors influence the effectiveness of the BioLSTM model in detecting network anomalies. The objective is to conduct a comprehensive comparative evaluation of the BioLSTM model against established anomaly detection methods, using metrics such as accuracy, precision, recall, and F1 score. The goal is to assess the effectiveness of the BioLSTM model in network anomaly detection relative to other existing approaches. The goal is to identify the optimal configuration of the BioLSTM model through systematic experimentation. This involves determining the ideal hyperparameters, including the number of epochs and batch sizes, with the objective of achieving peak accuracy in detecting network anomalies. This optimization process is crucial for enhancing the overall performance of the model. The objective is to derive meaningful insights from the project findings and offer actionable recommendations for enhancing network security. By understanding the strengths and weakness of the BioLSTM model and other anomaly detection methods, the goal is to contribute to the development of effective strategies for detecting and mitigating malicious activities in network environments. To implement this project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement this project, we have designed various steps in the flow of work. The first step is importing the packages. In this module, necessary Python libraries and packages are imported. We have imported pandas for data manipulation, NumPy for numerical operations, matplotlib and seaborn for data visualization, scikit-learn for machine learning, keras for building deep learning models, and Flask for web development. The next step is exploring the dataset. This module involves loading and exploring the NSL-KDD dataset. Initial steps include understanding the structure of the dataset, checking for missing values, and gaining insights into the distribution of different features. Data processing. Here, the raw dataset is converted into a pandas data frame for easier manipulation. The data is formatted into a structure that is suitable for Keras, which is a high-level neural networks API. Columns that are not relevant and that might introduce noise to the model are dropped. Here we convert binary classes to 0 and 1 for model compatibility. Visualization using seaborn and matplotlib. Utilizing Seaborn and Matplotlib, this module involves creating visualizations to better understand the dataset. This can include plots like histograms, paid plots, and heat maps to reveal patterns, correlations, and potential outliers. Label encoding using label encoder. Categorical data is often encoded into numerical format for machine learning models. The label encoder is applied to convert categorical labels into numerical values. Feature selection using select percentile. Feature selection is crucial for building efficient models. This module involves selecting the most relevant features using select percentile, which is a method based on statistical tests. Splitting the data into train and test. The dataset is split into training and testing sets. The training set is used to train the machine learning model, while testing set is reserved for evaluating its performance. Building the model. This module In this module, the machine learning and deep learning models are constructed. This involves defining the architecture of the neural network models. Training the model. The model is trained using the training dataset. This involves feeding the input data to the models and adjusting its parameters to minimize the difference between predicted and actual outcomes. Flask framework with SQLite for sign up and sign in. This module integrates Flask Web Framework with an SQLite database to implement a user sign up and sign in functionality. This involves creating routes and views for user registration and authentication. User gives input as feature values. User input feature values through the front end of the application. This information is then sent to the server for further processing. The given input is pre-processed for prediction. The received user input is pre-processed to ensure that it aligns with the requirements of the trained model. This involves cleaning, which is data cleaning, encoding, or scaling to match the format used in the during training. Trained model is used for prediction. The pre-processed input is fed into the trained machine learning model to make predictions. The model leverages the learned patterns from the training phase to provide an output based on the user's input. Final outcome is displayed through frontend. The predicted outcome is sent to the frontend and displayed to the user. This is in the form of classification result. Algorithms which are used in the project are CNN, which is convolutional neural network. It is a deep learning algorithm designed for processing structured grid data. It utilizes convolutional layers to automatically and adaptively learn spatial hierarchies of the features from the input data. CNNs are particularly effective in image related tasks where the lower layers learn basic features like edges and textures, and higher layers combine these features to recognize complex patterns. The next algorithm is BiLSTM with NADM. Bidirectional long short term memory. It is a type of recurrent neural network that processes sequences bidirectionally. NADM is an optimizer that combines the benefits of Nesterov accelerated gradient and ADAM optimization. BiLSTM is suitable for sequence data, making it relevant for tasks involving temporal dependencies such as analyzing network traffic patterns. NADM is chosen for its adaptive learning rates and momentum, potentially improving convergence. The next algorithm is BiLSTM with ADAM. ADAM is optimization algorithm that computes adaptive learning rates for each parameter, combining the benefits of both momentum and RMS prop. BiLSTM, as described earlier, it processes sequences bidirectionally. ADAM is widely used in deep learning tasks due to its adaptive learning rate properties. BiLSTM is suitable for capturing long range dependencies in sequential data, making it valuable for network anomaly detection. The next algorithm is BiLSTM with RMS prop. RMS prop is root mean square propagation. It is an optimization algorithm that adapts the learning rate for each parameter based on the magnitudes of recent gradients. It is combined with the bidirectional LSTM in this case. RMS prop can handle non-stationary environments, making it useful in scenarios where statistical properties of the data may change over time. This is beneficial for the network data that may exhibit varying parameters. The next algorithm is BiLSTM with ADAMAX. ADAMAX is a variant of ADAM optimizer that uses infinity norm, which is maximum absolute value of the path gradients. It is applied in conjunction with bidirectional LSTM. ADAMAX is similar to ADAM, which is effective for tasks with sparse gradients. BiLSTM with ADAMAX is chosen based on the adaptability of the ADAMAX in handling a variety of learning rate scenarios. The next algorithm is BiLSTM with SGD, which is stochastic gradient descent. It is a traditional optimization algorithm that updates model parameters based on the negative gradient of the loss function. It is used with bidirectional LSTM in the context. While SGD lacks some adaptive features of the new optimizers, it is computationally efficient. Its relevance in the project stem from specific scenarios where a simple optimizer is preferred. The next algorithm is LSTM with AdaGrad. AdaGrad is an optimization algorithm that adapts the learning rate for each parameter based on the historical gradient information. It is combined with the bidirectional LSTM. Adagrad is suitable for sparse data scenarios. In the project, it is chosen for based on the characteristics of the network data, where certain features may be more informative than others. The next algorithm is BiLSTM with FTRL, which is follow the regularized leader. It is an optimization algorithm designed for online tasks. It combines both gradient based learning and element regularization. It is used in conjunction with bidirectional LSTM. FTRL is useful in scenarios with large sparse datasets. In the project, it is chosen for its efficiency in handling potentially large and sparse nature of network data. As an extension, we applied an hybrid models to produce more robust and accurate final prediction. Also, as an extension, we built the front end using Flask framework for user testing with user authentication. We have evaluated the project using different performance metrics, which are accuracy, precision, recall, and F1 score. So here we have comparison graphs for all those metrics. This is accuracy comparison graph. Here on x-axis we have accuracy score for each algorithm, and on y-axis we have algorithm names. Accuracy is a measure of the overall correctness of the model. It calculates the ratio of correctly predicted instances to the total instances. This is precision score comparison graph. It is also known as positive predictive value. It is a measure of the accuracy of the positive predictions made by a model. It calculates the ratio of correctly predicted positive observations to the total predicted positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It measures the ability of the model to capture all relevant instances. It calculates the ratio of correctly predicted positive observations to the total actual positives. This is F1 score comparison graph. It is the harmonic mean of precision and recall, providing a balanced assessment of a model's performance. It is particularly useful when there is an uneven class distribution. The algorithm which performs well among all these metrics will be used for final prediction. To execute the project, first we need to open the code folder which contains source code files. So this is the code folder of the project. This is NSLKDD folder which contains dataset which is of NSLKDD, and we will use the dataset for training the algorithms. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. And these are the model files which contain the algorithm information and that will be loaded into the project code during runtime. Here we have notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the signup.db file which contains the database file, and that is used for storing the user information. And now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. And now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folder's path. Here we need to type the command python space app.py and then click on enter. This will compile app.py file and execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which will be the local host and the port unless configured differently. This is the local host and this is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser. And this web page is built by using the Flask framework. Here we can see a sign up link first. We need to click on that and enter all the sign up details if we are signing up newly. I have already signed up and have an account in it. So we'll directly sign in. For that, we need to click on sign in. Here we need to give our username and the password. So I'm giving my username and the password. And now click on login. We have logged in successfully. Here we are redirected to prediction page. We can see that we need to enter all these parameters. Based on the given parameters, we will get the prediction whether attack is detected or not. So now we will understand all these parameters. So here we have protocol type. It indicates the communication protocol used in the network traffic. Here we have service. It specifies the network service or application is associated with the traffic. Here we have SRC bytes. They are the number of bytes sent by the source in a network communication. Here we have destination bytes. These are the number of bytes received by the destination in a network communication. Here we have logged in. It indicates whether a user is logged in into a service or system. Here we have count. It is the total number of occurrences or the instances of a specific event or the condition. Here we have SRV count. It is the count of connections to a specific service or application. Here we have SRV different host rate. It is the rate at which different hosts connect to the same service. Here we have different host count. It is the count of different hosts involved in the communication. Here we have destination host SRV count. It is the count of connections to a specific service on a destination host. Here we have destination host same SRV rate. It is the rate at which destination host connects to the same service. Here we have destination host different SRV rate. It is the rate at which the destination host connects to the different services. Here we have destination host same SRC port rate. It is the rate at which destination host connects using the same source port. Here we have destination host SRV different host rate. It is the rate at which the destination host connects to the different host for a specific service. We have understood all the parameters. So now we will enter the parameters step by step. So the protocol type is 1, service is 22, SRC bytes are minus 0.002, destination bytes are minus 0.138, logged in value is 2.396, count is minus 1.52142, SRV count is minus 1.1566, SRV different host rate is minus 0.2036, different host count is minus 3.451, destination host SRV is minus 1.694, destination host same SRV is 0.599, destination host value is minus 0.2827, destination host same port is minus 1.02208, and destination host SRV different host rate is minus 0.15863. Now we need to click on predict. So here we got the prediction as there is no attack detected and it is normal. Now we will enter the parameters again but with the different values and see what will be predicted. Click on home. I have entered all the parameters. Now we will click on predict. Here we got the prediction as there is an attack detected and the attack type is DDoS or probe or R2L or U2R. In this way, if we enter the parameters, based on that we will get the prediction whether there is an attack detected or not. So now click on sign up. Conclusion of the project. The project successfully crafted a robust anomaly detection system for network data incorporating a blend of traditional machine learning and advanced deep learning methods such as LSTM and CNN. Through rigorous experimentation, the project determined optimal hyperparameters using various optimizers like NADAM, ADAM, RMS-prop, ADAMAX, SGD, ADAGRAD, and FTRL. This fine-tuning significantly improved the accuracy and efficiency of the BiLSTM model. The project conducted a comprehensive evaluation comparing the performance of BiLSTM model against established anomaly detection methods. Precision metrics like accuracy and F1 score were employed for a holistic examination. By integrating Flask and SQLite, The project achieved a seamless user interface. This allowed users to input feature values, subsequently processed by the trained by LSTM model, delivering a user friendly experience. The project's findings offer meaningful insights and actionable recommendations to bolster network security. These insights provide valuable guidance for future advancements in cybersecurity practices.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.